Imagine you're in a spaceship, traveling at 99% the speed of light. You turn on your headlights. Common sense says the light should shoot out at the speed of light plus your ship's speed, right? Wrong. The light from your headlights still travels at exactly 299,792,458 meters per second. Not a single meter per second faster. And here's what will absolutely shatter your understanding of reality. If someone standing still measured that same light beam, it also measured at exactly 299,792,458 meters per second. The same speed. From both perspectives, simultaneously. This isn't a magic trick. This is the universe we actually live in. And the reason why light has this cosmic speed limit is so profoundly strange that once you understand it, you'll never see reality the same way again. Because here's the twist. Light doesn't have a speed limit. You do. Space does. Time does. Light is just showing us the truth about the fabric of existence itself. What if I told you that the speed of light isn't really about light at all? That it's actually the maximum speed of causality itself, the rate at which cause and effect can propagate through the universe? What if every single thing you think you know about how the universe works is based on a fundamental misunderstanding of what speed, distance, and time actually are? By the end of this video, you're going to understand why the speed of light isn't just some random cosmic speed limit, but rather an unavoidable consequence of the deepest structure of space-time itself. And trust me, once you see it, you can't unsee it. But before we dive into this mind-bending journey, smash that like button if you're ready to have your understanding of reality completely rewired. And drop a comment telling me what country you're watching from and what time it is where you are right now. I'm genuinely curious how far across the globe this cosmic truth is spreading. And subscribe, because we're about to go deep into the most profound mystery in physics, and you won't want to miss what's coming. Let's start with what seems like a simple question. What is speed? You probably learned in school that speed is distance divided by time. If you drive 60 miles in 1 hour, your speed is 60 miles per hour. Simple, right? Here's the first crack in your understanding of reality. This definition assumes that distance and time are absolute, unchanging backdrops against which things move. They're not, but we're getting ahead of ourselves. Let's build this properly. For thousands of years, humans assumed there was no speed limit in the universe. If you threw a ball at 10 miles per hour from a cart moving 20 miles per hour, the ball would travel at 30 miles per hour. Speeds just add up. This is called Galilean relativity, named after Galileo Galilei, who formalized these ideas in the early 1600s. And for everyday life, it works perfectly. Then came light. In 1676, a Danish astronomer named Ole Rekner made one of the most important observations in the history of science. He was studying Jupiter's moon Io, timing its eclipses as it passed behind Jupiter. He noticed something bizarre. The eclipses happened earlier than expected when Earth was moving toward Jupiter, and later when Earth was moving away. The only explanation? Light had a finite speed, and it took time to reach us across the varying distances. Think of it like this. Imagine you're standing at a train station, and trains arrive every exactly 10 minutes. Now imagine you start walking toward the direction the trains are coming from. You'll encounter trains more frequently, maybe every 9 minutes, because you're moving toward them. Walk away from them, and they'll arrive less frequently, maybe every 11 minutes. Rekner saw this effect with light from Io's eclipses. The trains were light signals, and Earth's motion was changing how frequently we receive them. Rekner calculated light traveled at about 220,000 kilometers per second. Not bad for 1676, considering the actual value is about 300,000 kilometers per second. The key insight wasn't the exact number. It was the revelation that light didn't travel instantaneously. Over the next 2 centuries, scientists got better at measuring light speed, but they assumed light was like sound. something that needed a medium to travel through. Sound travels through air at about 343 meters per second. Underwater, it's faster, about 1,480 meters per second. In steel, even faster still. So scientists assumed light must travel through some invisible medium they called the luminiferous ether, a substance that permeated all of space. Here's where things get interesting. If light travels through this ether, then the Earth must be moving through it as we orbit the Sun. Just like walking through wind, we should measure different speeds of light depending on which direction we're moving through this ether. In 1887, two American physicists, Albert Michelson and Edward Morley, designed an ingenious experiment to detect Earth's motion through the ether. They split a beam of light, sent the two beams in perpendicular directions, bounced them off mirrors, and brought them back together. If Earth was moving through the ether, one beam should take slightly longer than the other, because it would be fighting against the ether wind in one direction. The difference would be tiny, but their instrument was sensitive enough to detect it. The result? Nothing. No difference whatsoever. They repeated the experiment at different times of year when Earth was moving in different directions through space. Still nothing. The speed of light was exactly the same in every direction, regardless of how Earth was moving. This shouldn't have been possible. Imagine you're on a train moving at 60 miles per hour, and you throw a ball forward at 20 miles per hour. Someone standing still watching you would measure the ball moving at 80 miles per hour, your speed plus the ball's speed. But light didn't work this way. No matter how fast you were moving, light always traveled at the same speed relative to you. Scientists were baffled. Some tried to explain it by suggesting Earth dragged the ether along with it. Others proposed increasingly complex modifications to the ether theory. But nothing worked. The experimental result was undeniable. The speed of light was constant, regardless of the motion of the source or the observer. This is where Albert Einstein enters our story. In 1905, at age 26, working as a patent clerk in Switzerland, Einstein did something radical. He didn't try to explain away the Michelson-Morley result. He accepted it as a fundamental truth and asked, what if the speed of light is actually constant for everyone, no matter how they're moving? What would that mean for the universe? The answer would change everything. Here's where your mind is about to be blown for the first time. If the speed of light is constant for everyone, then something else has to give. And that something is time and space themselves. Let me show you why this is unavoidable. Imagine you're standing on a train platform, and a train passes by at half the speed of light. On the train, someone shines a flashlight from the floor to the ceiling. From their perspective on the train, the light goes straight up and straight down. The distance is, let's say, 3 meters. And since light travels at 300,000 kilometers per second, the light takes a tiny fraction of a second to make the journey. Now, from your perspective standing on the platform watching this train zoom by, what do you see? You see the light beam traveling diagonally. It goes up, sure, but it's also moving horizontally because the train is moving. The light traces out a diagonal path, which is longer than the straight up and down path the person on the train sees. Here's the critical part. Light travels at the same speed for both of you. That's not negotiable anymore. That's what experiments have proven beyond any doubt. Same speed means that if the light travels a longer distance from your perspective, it must take more time. Think of it like this. Imagine two runners running at exactly the same speed, but one takes a straight path and the other takes a zigzag path. The one taking the zigzag path takes longer to reach the finish line, not because they're running slower, but because they're covering more distance. For light, the speed can't change. So if the distance is longer, the time must be longer. This means time on the moving train is passing more slowly than time on the platform. Not because of any mechanical effect or some quirk of measuring devices. Time itself is actually, genuinely, physically passing at a different rate. Einstein called this time dilation. And here's what will really bake your noodle. It's not an illusion or a measurement error. Both perspectives are equally valid. From the person on the train's perspective, their time is normal and yours is weird. From your perspective on the platform, your time is normal and theirs is weird. There's no absolute reference frame that determines who's really experiencing normal time. Both of you are correct within your own frame of reference. This is special relativity, Einstein's 1905 theory that revolutionized physics. The math is actually quite elegant. If you're moving at velocity v, time for you, as measured by someone standing still, slows down by a factor of the square root of 1, v squared per c squared, where c is the speed of light. This factor is called the Lorentz factor, named after Hendrik Lorentz, who actually derived these mathematical transformations before Einstein, but didn't understand their physical meaning. At everyday speeds, this factor is so close to 1 that you'd never notice. At 60 miles per hour, your time is slowed by about 0.0000000000001%. But as you approach the speed of light, the effect becomes dramatic. At 90% the speed of light, time slows to about 44% of normal. At 99% the speed of light, time slows to about 14% of normal. And at the speed of light itself, the Lorentz factor becomes infinite. Time would stop completely. But it gets weirder. Space itself also changes. From your perspective on the platform, not only is time on the train passing more slowly, but the train itself is physically shorter in the direction of motion. This is called length contraction. The train is actually physically compressed. Again, this isn't an optical illusion. The train genuinely occupies less space along its direction of motion. And here's the kicker that really demonstrates why light's speed is constant. From the train's perspective, it's not the train that's contracted. It's the platform and everything on it that's compressed. Each observer sees the other's space contracted and time dilated. Both are correct. This resolves our original puzzle. When you're on that spaceship traveling at 99% the speed of light and you turn on your headlights, the light travels away from you at the speed of light from your perspective. But from the perspective of someone standing still, your time is running slowly and your space is contracted in just the right amounts so that when they measure that same light beam, they also get the speed of light. The numbers work out perfectly every single time because time and space adjust themselves to keep light's speed constant. Reality is far stranger than we imagined. Speed isn't just distance over time. Speed is a relationship between space and time, and space and time are flexible, moldable things that change based on motion. The only thing that remains constant, the one invariant feature of the universe, is the speed of light. But here's the question that should be burning in your mind right now. Why? Why is the universe built this way? Why does the speed of light have to be constant? What's so special about this particular speed? The answer is going to blow your mind even more than what you've just learned. Let's stop calling it the speed of light for a moment, because that name is misleading. It makes it sound like light is special, like there's something unique about photons that determines this cosmic speed limit. But that's not what's really going on. What we call the speed of light is actually the maximum speed at which any information, any cause and effect relationship, any influence whatsoever can propagate through the universe. It's the speed of causality itself. Light just happens to travel at this speed because photons have zero mass. But anything with zero mass travels at this speed. Gravitons, the hypothetical particles that carry gravitational force, should also travel at this speed. And here's the really profound part. This speed limit exists whether or not light exists. Think about what speed really means in the deepest sense. When you say something moves from point A to point B, you're describing a causal relationship. The object was at A, and then later it was at B, cause and effect, connected across space and time. The cosmic speed limit is the maximum rate at which these causal connections can happen. Here's an analogy. Imagine the universe as a gigantic computer, and space-time is the processor. There's a maximum clock speed to this processor, a maximum rate at which it can update. It can't process cause and effect relationships faster than this maximum rate. That maximum rate manifests to us as the speed of light, but it's really about how quickly the universe can compute reality itself. But why is there a maximum at all? Why isn't causality instantaneous? Here's where we need to talk about something called space-time. Before Einstein, everyone thought of space and time as separate things. Space was the three-dimensional stage where events happened, and time was a separate dimension that flowed uniformly for everyone. Einstein showed that this is wrong. Space and time are unified into a single four-dimensional structure called spacetime. In spacetime, everything that has ever happened or will ever happen already exists in a sense. Your entire life, from birth to death, is a four-dimensional structure called your world line. It's like a tube threading through spacetime, with one end at your birth and the other end at your death, and every moment of your existence somewhere along that tube. When you move through space, you're actually rotating in spacetime. Imagine spacetime as a four-dimensional graph, where three axes represent space, left-right, forward-backward, up-down, and one axis represents time. When you're standing still in space, you're moving through time at the maximum rate, 1 second per second. But when you start moving through space, you're tilting your path through spacetime. You're now moving partially through space and partially through time. The faster you move through space, the more you're tilting your world line, and the slower you move through time. Here's the crucial insight. The total motion through spacetime is always the same. You're always moving through spacetime at exactly the speed of light. Always, right now. As you sit watching this video, you are moving through time at the speed of light. When you get up and walk around, you're moving through a combination of space and time, but your total motion through spacetime is still the speed of light. Think of it like this. Imagine you're walking north at 3 miles per hour. Then you turn and start walking northeast instead. You're now moving north at maybe 2 miles per hour and east at 2 miles per hour, but your total speed is still about 3 miles per hour. It's just divided between two directions now. In spacetime, you're always moving at the speed of light, but that motion can be divided between motion through space and motion through time in different proportions. Light, with its zero mass, travels entirely through space and not at all through time. From a photon's perspective, if photons had perspectives, no time passes at all. A photon emitted from a star 1 billion light years away and entering your eye right now experiences zero elapsed time between emission and absorption. Its entire journey is instantaneous from its own reference frame. This is why nothing with mass can reach the speed of light. To reach the speed of light, you would have to tilt your world line completely into the space directions and completely out of the time direction. Your motion through time would have to reach zero, but you exist in time. You have a past and a future. To reach the speed of light would mean becoming timeless, which is impossible for anything that has mass, anything that has a duration of existence. Hermann Minkowski, one of Einstein's former mathematics professors, put it beautifully in 1908. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Space and time aren't separate. They're aspects of a unified spacetime, and the speed of light is the conversion factor between them, the fundamental exchange rate between space and time. In the mathematics of spacetime, developed by Minkowski, the speed of light is often set to 1. This isn't just for convenience. It reflects the deep truth that space and time are measured in the same units. 1 second equals 299,792,458 meters. Time is distance. Distance is time. They're the same thing measured in different directions in spacetime. But we still haven't answered the ultimate question. Why does spacetime have this structure? Why is there a maximum speed of causality at all? Why is the universe built this way? To answer that, we need to go even deeper. What if I told you that the speed of light being finite is the only way the universe could possibly be consistent? That if information could travel instantaneously, reality itself would be paradoxical and couldn't exist? Let me show you why. Imagine for a moment that information could travel faster than light. Let's say you have a magical faster-than-light telephone that lets you send messages instantaneously across any distance. You're on Earth, and your friend is on a spaceship, traveling away from Earth at 80% the speed of light. You pick up your FTL phone and send a message. From your perspective, the message arrives instantly. But here's the problem. From your friend's perspective on that spaceship, because of relativity, events that are simultaneous for you are not simultaneous for them. The geometry of space-time means that what you perceive as right now on their ship is actually their future. And what they perceive as right now on Earth is actually your past. So when you send that instantaneous message to their future, and they instantly reply back to your past, you can receive their reply before you sent your original message. You've created a closed loop in time, a genuine causality paradox. You could use this to send messages to yourself in the past. Think of it like this. Imagine you're looking at a map and you draw two dots on it. From one angle, the dots look like they're side by side. From another angle, rotated a bit, one dot looks higher than the other. Simultaneity in spacetime is like that. What counts as, at the same time, depends on your reference frame, your angle through spacetime. If you could send signals that don't respect this structure, you could route them in a loop that arrives before it was sent. The only way to prevent this paradoxical situation is to have a maximum speed for information transfer. That maximum speed creates what's called a light cone. From any event in spacetime, there's a boundary separating the events that can be causally influenced by that event and events that can't. That boundary expands outward at the speed of light. Everything inside your past light cone could have influenced you. Everything inside your future light cone can be influenced by you. But events outside your light cone are causally disconnected from you. They can't affect you, and you can't affect them. Not yet, at least. Not until your light cones expand enough to overlap. This is profound. The speed of light doesn't just limit how fast things can move. It defines the very structure of causality itself. It determines what can influence what can be connected to what. Without this limit, cause and effect would be meaningless concepts. The universe would be paradoxical. Julian Barber, a British physicist who has spent his career thinking about the nature of time, argues that time itself emerges from the causal structure of the universe. Time isn't some pre-existing stage that things move through. Time is the ordering of causes and effects, and that ordering is defined by light cones. The speed of light is, in a sense, the speed of time itself. But let's go even deeper. Why is the speed of light 299,792,458 meters per second specifically? Why not twice as fast or half as fast? Here's where things get really wild. It doesn't matter. The specific number is arbitrary, an accident of what we chose to call a meter and a second. What matters is the ratio, the relationship between space and time. We could redefine our units to make the speed of light anything we want. In natural units, which physicists often use, the speed of light is simply one. 1 unit of space equals 1 unit of time. The deep question isn't why light has the speed it has, but why space and time are connected at all. Why they form this unified space-time structure with a finite exchange rate between them. And here's a mind-blowing thought. What if they have to be? What if space-time with its finite speed of causality is the only logically consistent possibility? Some theoretical physicists working on quantum gravity and the fundamental structure of reality are exploring the idea that spacetime itself might emerge from something more fundamental, perhaps quantum entanglement or information theory. In these approaches, the speed of light isn't put in by hand as a postulate. It emerges naturally from the deeper structure. Imagine the universe is fundamentally made of bits of information, like a cosmic computer. These bits can be connected to each other, correlated with each other, but there's a limit to how quickly information can propagate from one bit to its neighbors. That propagation limit, emerging from the fundamental discreteness of information itself, would manifest as a cosmic speed limit. The speed of light would be a consequence of the universe having a finite information density. This is speculative, cutting-edge stuff that hasn't been proven yet, but it points to a profound possibility. The speed of light might be the way it is because that's simply how reality has to work. A universe with instantaneous information transfer might be logically impossible, a mathematical contradiction that can't exist. The speed of light isn't a law that the universe obeys. It's a feature of what a universe even is. Now we need to talk about why things with mass can't reach the speed of light. This is where Einstein's most famous equation comes in. E equals mc. Most people know this equation, but few understand what it really means. It's usually interpreted as mass can be converted into energy, which is true, but misses the deeper point. What this equation really says is that mass and energy are the same thing. Mass is energy. Energy is mass. They're not two different entities that can be converted into each other. They're two different ways of measuring the same underlying thing. Think of it like temperature and molecular motion. When we say something is hot, we're really saying its molecules are moving quickly. Temperature isn't a separate thing that causes molecular motion. Temperature is molecular motion, measured in a particular way. Similarly, mass is a form of energy, or more precisely, mass is the name we give to energy when it's not moving, when it's at rest in our reference frame. The full equation, which Einstein derived, is actually E squared equals mc squared squared plus pc squared, where p is momentum. For an object at rest, p equals 0. This reduces to E equals mc. But when the object is moving, it has additional energy from its motion. Here's what happens as you try to accelerate something closer and closer to the speed of light. It takes more and more energy. Not just more energy proportionally, but increasingly more energy. The Lorentz factor I mentioned earlier, that square root of 1v squared per c squared in the denominator, appears in the equations of motion. As v approaches c, that factor approaches 0, which means the energy required approaches infinity. To accelerate a single electron to exactly the speed of light would require infinite energy. Not a really large amount of energy, literally infinite. All the energy in the universe wouldn't be enough. It's not a technological limitation. It's a fundamental feature of how reality works. But why? What's really happening here? Remember that mass and energy are the same thing. When you add energy to something by accelerating it, you're adding to its mass energy. At speeds close to the speed of light, most of the energy you're adding doesn't make the object go faster. Instead, it increases the object's relativistic mass, making it harder to accelerate further. Think of it like this. Imagine you're pushing a snowball up a hill, and as you push, the snowball gets larger and heavier. The faster you push it, the more rapidly it gains size and weight. Eventually, you're putting all your effort into just maintaining speed against the ever-increasing weight, with almost none going into making it faster. That's what happens when you try to accelerate something to light speed. The energy you add just makes it heavier in a relativistic sense, requiring even more energy to accelerate further. From the perspective of space-time geometry, here's what's happening. Objects with mass always travel through space-time at exactly the speed of light, as I mentioned before. Right now, you're traveling through time at very close to the speed of light, and through space very slowly. When you accelerate through space, you're tilting your path through spacetime. But you can only tilt so far. Reaching the speed of light through space would require tilting your world line completely horizontal, which would mean zero motion through time. For an object with mass, with a duration, this is impossible. It would be like trying to rotate a three-dimensional object into flatness. The dimension can't just disappear. Particles without mass, like photons, don't have this problem. They have energy and momentum, but their rest mass is exactly zero. They exist only in motion, only traveling through space, never through time. They're always on the boundary, always at the speed of light. They can never be brought to rest from any reference frame. This connects to something beautiful about the universe. The speed of light is also the speed of masslessness. Anything that has zero rest mass must travel at the speed of light. Anything that has non-zero rest mass must travel slower than the speed of light. The two facts are intimately connected. Here's something that will really bake your noodle. Gravity itself propagates at the speed of light. If the sun suddenly vanished right now, we wouldn't feel the change in gravitational pull for about 8 minutes, the same time it takes light to reach us from the sun. This was predicted by Einstein's general theory of relativity from 1915 and has been confirmed by observations of gravitational waves from colliding black holes, detected for the first time in 2015 by LIGO, the Laser Interferometer Gravitational Wave Observatory. Those detections, by the way, won the 2017 Nobel Prize in Physics for Rainer Weiss, Mary Barish, and Kip Thorne. When two black holes spiral into each other and merge, they create ripples in spacetime itself that radiate outward at the speed of light. These ripples are incredibly faint by the time they reach Earth, stretching and squeezing space by less than the width of a proton. But LIGO detected them, confirming that gravity, like light, respects the cosmic speed limit. Everything respects this limit. All forces, all influences, all information. The structure of spacetime imposes this limit on all of reality. Let's bring this back to Earth for a moment. What does all this actually mean for the real world? How does the finite speed of light affect us? The most obvious consequence is that we can never travel faster than light, which means the universe is much larger than we can ever explore. The observable universe is about 93 billion light years in diameter. Even if we could travel at 99.9999% the speed of light, which we can't, most of the universe would remain forever out of reach because it's expanding faster than we could travel to it. But there are more subtle consequences that affect us right here and now. GPS satellites, for instance, have to account for both special and general relativity. Each satellite orbits Earth at about 14,000 kilometers per hour, and at that speed, time on the satellite runs slightly slower than time on the ground because of special relativity. But the satellites are also higher up in Earth's gravitational field, where general relativity says time runs slightly faster. The two effects partially cancel out, but there's still a net difference of about 38 microseconds per day. That might not sound like much, but GPS works by timing how long it takes radio signals traveling at the speed of light to reach your phone from multiple satellites. Location is calculated from these timing differences with nanosecond precision. If we didn't account for relativistic effects, GPS would drift by about 10 kilometers per day and become useless within minutes. Every time you use your phone to navigate, you're relying on Einstein's theories being correct. The speed of light being constant and time being relative aren't just abstract physics concepts. They're built into the technology you use every day. Particle accelerators, like the Large Hadron Collider near Geneva, Switzerland, accelerate protons to 99.9999991% the speed of light. At this speed, time dilation is so extreme that from the proton's perspective, it lives about 7,000 times longer than it would at rest. The entire 27-kilometer ring of the accelerator is contracted down to just a few meters from the proton's reference frame. Engineers designing these machines have to account for all these relativistic effects, or the particles would crash into the walls. But here's something even more mind-blowing. The reason matter is stable, the reason your body doesn't fall apart or explode, is ultimately connected to the finite speed of light and the structure of spacetime. Atoms are held together by the electromagnetic force between positive nuclei and negative electrons. This force is carried by photons, virtual particles that pop in and out of existence, mediating the electromagnetic interaction. These virtual photons respect the speed of light limit. The electromagnetic force can't act instantaneously. It takes time, limited by the speed of light, for the force to propagate. If the speed of light were infinite, if forces could act instantaneously, the mathematical equations describing atoms would break down. The structure of matter, as we know it, might not be stable. The finite speed of light, by creating a delay in how forces propagate, is essential to the stability of matter itself. You exist because light has a speed limit. Here's another practical consequence. Simultaneity is relative, which means that for events far apart in space, there's no absolute answer to the question, which happened first? If you're watching two fireworks explode on opposite sides of town, and they look simultaneous to you, someone driving quickly past might see one explode before the other. Both of you are correct. There's no privileged reference frame that determines the true order of events. The only events that have an absolute order are those that can be causally connected, events where one is inside the other's light cone. If event A can influence event B, then all observers agree that A happened before B. But if A and B are outside each other's light cones, if they're separated by too much space and too little time for light to travel between them, then their order is ambiguous. Different observers will disagree about which came first, and all of them are equally correct. This has profound implications. It means there's no universal, now, extending across the universe. The present moment doesn't exist as a cosmic phenomenon. My now and your now overlap if we're close together, but an alien on a planet a million light years away has a now that's completely different from ours. What they consider simultaneous with this moment might be a million years in our past or future, depending on how they're moving relative to us. Time is not a cosmic river flowing uniformly everywhere. Time is local, personal, dependent on motion and position. The only universal structure is the light cone structure, the pattern of what can influence what. Now let's talk about quantum mechanics, because this is where things get truly weird. Quantum mechanics seems to violate the cosmic speed limit, but in a very subtle way that doesn't actually break causality. In quantum mechanics, particles can be entangled. When two particles are entangled, they share a quantum state such that measuring one instantly affects the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, and thought it proved quantum mechanics must be incomplete. In 1964, physicist John Stuart Bell derived a mathematical theorem showing that no local hidden variable theory could reproduce quantum mechanics predictions. Experiments testing Bell's theorem, the first convincing ones done by Elling Aspect in the early 1980s, confirmed that quantum entanglement is real. When you measure one particle, the other particle's state really does change instantaneously, faster than light. So does this mean quantum mechanics violates the speed limit? Does information travel faster than light through entanglement? The answer is no, and understanding why is crucial to understanding what the speed of light limit really means. When two particles are entangled, measuring one gives you information about the other instantly. And this is the critical part, you can't use this to send information faster than light. Here's why. The result you get when you measure your particle is random. You can't control it. You can't decide to measure spin up or spin down. You just get a random result. The person measuring the other particle also gets a random result, but their results are correlated with yours. To know that your results are correlated, you have to compare notes, and that comparison has to be done through normal, slower-than-light communication. You can't know that the measurement has affected the distant particle until you communicate through conventional means. Think of it like this. Imagine you and a friend each have a magic coin. When you flip your coin and it comes up heads, your friend's coin instantly becomes tails, no matter how far apart you are. That's entanglement. But you can't choose whether to get heads or tails. It's random. Your friend also gets a random result. Only when you call each other and compare results do you discover the correlation. The phone call transmits information. The entanglement doesn't. Entanglement creates correlations, but correlations aren't information transfer. To have information transfer, you need to send a message, encode a signal, transmit meaning. That always requires something to travel from sender to receiver, and that something is limited to the speed of light. The way physicists put it is that entanglement doesn't violate locality in the right way to allow faster-than-light signaling. The speed of light limit is really about the speed of signals, the speed at which you can cause something to happen at a distance. Entanglement doesn't let you do that. But here's what's profound about this. Quantum mechanics respects the light cone structure of spacetime. Entanglement can create correlations between events outside each other's light cones, but those correlations can't be used to send signals between them. Cause and effect still respects the speed limit, even in quantum mechanics. Some physicists argue that this hints at something deep about the relationship between quantum mechanics and spacetime. Maybe entanglement is more fundamental than spacetime itself. Maybe spacetime emerges from entanglement patterns. If that's true, then the speed of light would be a consequence of quantum entanglement structure, an emergent feature of how quantum correlations work. This is cutting-edge theoretical physics, explored by people like Juan Maldacena at the Institute for Advanced Study and Mark van Ramsdonk at the University of British Columbia, who've shown mathematical connections between entanglement and spacetime geometry. The technical term is A=EPR, connecting Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen pairs, entangled particles. The idea is that two entangled particles might be connected by a tiny wormhole in a higher dimensional space, and that spacetime itself might be woven from threads of quantum entanglement. If this is true, and it's a big if, then the speed of light isn't a fundamental constant imposed on the universe. It's an emergent property, something that appears when you have enough entanglement threads woven together to create the fabric of spacetime. The limit exists because of how information is structured in quantum mechanics at the deepest level. But here's what really blows my mind. Whether spacetime is fundamental or emergent, whether the speed of light is a basic axiom or a consequence of something deeper, the end result is the same. Reality has a maximum speed for causality. The universe has a speed limit built into its very structure, and that limit is what makes cause and effect, time, space, and existence itself possible. Let's step back from the equations and the experiments for a moment and talk about what this really means for you, for your understanding of existence. The speed of light being finite means that when you look at anything, you're seeing into the past. When you look at your hand, you're seeing it as it was nanoseconds ago, the time it took light to travel from your hand to your eyes. When you look at the moon, you're seeing it as it was 1.3 seconds ago. The sun, 8 minutes ago. The nearest star, Proxima Centauri, 4.2 years ago. When you look up at the night sky, you're not seeing the universe as it is now. You're seeing a time machine, a window into different eras of cosmic history. That faint galaxy you can barely see through a telescope, you're seeing it as it was millions or even billions of years ago. The light left that galaxy when Earth was young, traveled across the expanding universe for eons, and finally arrived at your eye tonight. Some of the stars you see might not exist anymore. They may have exploded, collapsed into black holes, or faded into darkness. but their light is still reaching you, carrying the message of their ancient existence. You're receiving mail from the past. But here's the flip side that really messes with your head. From the perspective of a photon traveling from that distant galaxy to your eye, no time passes at all. The photon is emitted and absorbed in the same instant, from its own reference frame. The entire journey, billions of years from our perspective, is instantaneous from the photon's perspective. Think about what this means. Every photon that hits your eye, whether it came from your computer screen a few nanoseconds ago or from a distant galaxy billions of years ago, experienced zero elapsed time in transit. From the photon's perspective, it's always connected directly to where it was emitted. The source and destination are the same event. In a sense, when you see that ancient galaxy, you're not separated from it. The photon creates a direct connection through spacetime, a timeless link between the galaxy's past and your present. You're touching the past with your eyes. This is profound when you really sit with it. The speed of light being finite means that the past isn't gone. It's still out there, encoded in light, traveling through space. The universe has a memory, written in photons, spreading outward at the cosmic speed limit. And here's something that might comfort you or terrify you. Every moment of your life is also becoming part of this cosmic memory. Light from your first birthday is now 20 or 30 or 50 light years away, depending on your age, carrying information about that moment. In principle, an alien civilization with a powerful enough telescope, looking at Earth from 20 light years away right now, could watch you being born, not a recording. The actual light from that event, finally reaching them after 2 decades of travel. The past isn't just prologue. It's physically real, still existing in the photons, carrying its information outward through the cosmos. You're not just living in the present moment. You're creating a light-speed, expanding bubble of information that will propagate through the universe potentially forever, unless it's absorbed or scattered along the way. Now think about the future. The finite speed of light means there are events happening right now in distant parts of the universe that can't affect you yet. Their light hasn't reached you. You are causally disconnected from them. From your perspective, they haven't happened yet in any meaningful sense, because they can't influence anything in your light cone. But here's the really wild part. Because of relativity, different observers moving at different speeds will disagree about whether those events have happened yet. An alien zooming past Earth at high speed might consider events that are in your future to be in their past, and vice versa. The entire notion of now, spreading across the universe, is an illusion. There's no cosmic present moment. There's only the local present. You're sliced through spacetime, and it's different for everyone. This means that in a very real sense, the future already exists in spacetime, just as much as the past does. From a four-dimensional perspective, from the block universe view that relativity suggests, your entire life past, present, and future exists as a complete structure in spacetime. The feeling that only now is real is a feature of your consciousness moving through time, not a feature of the universe itself. Does this mean free will is an illusion? That's a philosophical debate that's beyond the scope of this video. But here's what physics says. Even if the future exists in spacetime, you can't access information from it. Causality flows forward in time within your light cone. The future is real in the mathematical structure of spacetime, but it's inaccessible to you now, and your choices still shape which particular world line you trace through that structure. The finite speed of light protects the arrow of time, the distinction between past and future. If information could travel faster than light, you could have time loops, signals arriving before they're sent, effects preceding causes. The cosmic speed limit is what makes the universe make sense, what prevents paradoxes, what keeps the story of existence coherent. Let's talk about the most frustrating consequence of the speed limit. It makes the universe mostly unreachable. The observable universe is huge, about 93 billion light years in diameter. But the vast majority of it is forever beyond our reach, not because of technological limitations, but because of the expansion of space itself, combined with the speed of light limit. Space is expanding, and distant parts of space are expanding away from us faster than light. Wait, didn't I just say nothing can go faster than light? Here's the loophole. Nothing can move through space faster than light, but space itself can expand at any rate. The speed limit applies to motion through space, not the expansion of space itself. Galaxies more than about 15 billion light-years away are receding from us faster than the speed of light because the space between us and them is expanding so rapidly. Light from those galaxies is still moving toward us at the speed of light, but space is expanding faster than the light can traverse it. It's like running on a treadmill that's accelerating faster than you can run. You're moving forward at your maximum speed, but you're still going backward relative to the room. This creates what's called the cosmological event horizon. There are galaxies so far away that their light will never reach us, not because they're too far for light to travel in the age of the universe, but because space is expanding too fast for their light to ever arrive. These galaxies are outside our cosmological light cone. We can never see them, never communicate with them, never visit them. They're forever beyond our reach. And it gets worse. The expansion of space is accelerating, driven by something we call dark energy that we don't really understand. This means that over time, more and more galaxies will slip beyond our cosmological event horizon. The visible universe is shrinking in terms of what we can ever reach. In the far future, trillions of years from now, if any civilizations still exist, they'll look out and see only their local group of gravitationally bound galaxies. Everything else will have receded beyond the horizon. They'll have no way to know that billions of other galaxies once existed. The evidence will have literally flown away faster than light. We're living in a special time, cosmologically speaking. We can still see the cosmic microwave background radiation from the Big Bang. We can still observe distant galaxies and study the history of the universe. Future observers won't have that privilege. The speed of light, combined with cosmic expansion, is creating a bubble of isolation around each galaxy cluster. But here's a thought that might blow your mind. What if faster than light travel is possible in ways we haven't discovered yet? Not moving through space faster than light, which is impossible, but manipulating space itself. General relativity allows for some pretty exotic possibilities. Wormholes, hypothetical tunnels through spacetime, could potentially connect distant parts of the universe. You'd travel through normal space at slower than light speeds, but you'd use a shortcut through a higher dimension. The Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994, describes how you could theoretically compress space in front of a spacecraft and expand it behind, creating a warp bubble that carries the ship faster than light from the perspective of external observers, even though the ship itself isn't moving faster than light through the space inside the bubble. The catch? These solutions require exotic matter with negative mass energy, something we've never observed and that might not exist. They also require enormous amounts of energy, potentially more than exists in entire stars. And there are theorems suggesting that any warp drive would inevitably create a time machine, allowing travel to the past, which creates all those causality paradoxes we want to avoid. Most physicists think these exotic space-time geometries, while mathematically allowed by general relativity, are probably not physically realizable. The universe seems to have built-in protections against causality violations, mechanisms that prevent time travel and faster-than-light signaling, even when the equations technically allow them. There's even a conjecture called the chronology protection conjecture, proposed by Stephen Hawking, suggesting that the laws of physics prevent time travel and the creation of closed time-like curves. It's not proven, but the fact that we've never observed causality violations suggests the universe really does enforce its speed limit rigorously. So we're probably stuck. The speed of light is probably a genuine, insurmountable barrier. The universe is vast beyond imagination, filled with trillions of galaxies, each with billions of stars, and we're confined to a tiny bubble of space we can ever hope to explore. We can see much of the universe, watch its light arriving from the depths of space and time, but we can never go there. We're like prisoners in a cosmic cell, free to look out the window but never to leave. Unless we're missing something fundamental. Unless there's some deeper understanding of physics that allows us to transcend this limitation. But honestly, probably not. The speed of light limit seems deeply woven into the fabric of reality itself. Now let's talk about what happens at the most extreme edges of spacetime. Black holes. Because black holes take the speed of light limit and push it to its most dramatic consequences. A black hole is a region of spacetime where gravity is so intense that nothing, not even light, can escape. The boundary of this region is called the event horizon. Once you cross the event horizon, you cannot come back, ever. You would have to travel faster than light to escape, and we know that's impossible. But here's what's really mind-bending. The event horizon isn't a physical barrier. There's nothing there, no wall or membrane. It's purely a geometric feature of spacetime. It's the boundary where spacetime is curved so severely that all paths forward lead inward. The speed of light isn't fast enough to climb out of the gravitational well. From the perspective of someone falling into a black hole, crossing the event horizon feels like nothing special. You pass through it at some fraction of the speed of light, and from your perspective, everything seems normal. You don't hit a wall. You just keep falling. But from the perspective of someone watching you from outside, they never see you cross the horizon. As you approach it, time dilation becomes more and more extreme. The light from your body becomes increasingly red-shifted, stretched to longer and longer wavelengths, dimmer and dimmer. To the outside observer, you appear to freeze in time, asymptotically approaching the horizon, but never quite reaching it, your image fading to darkness. Both perspectives are correct. From your perspective, you cross the horizon and continue falling. From the outside perspective, you never cross it. This isn't a contradiction. It's relativity. Different observers have different, but equally valid perspectives on spacetime events. And here's something truly bizarre. Once you've crossed the event horizon, the direction to the singularity at the center of the black hole isn't a direction in space anymore. It's a direction in time. Moving toward the singularity isn't a choice. It's as inevitable as moving from the past to the future. You can no more avoid hitting the singularity than you can avoid arriving at next Tuesday. The singularity is in your future, not in your spatial direction, and you will hit it in a finite amount of your personal time, typically within seconds for a stellar mass black hole, or hours for a supermassive black hole like the one at the center of our galaxy. Why is this? Because inside the event horizon, spacetime is so severely curved that the roles of space and time literally swap. The radial direction toward the center becomes time-like, and time becomes space-like. The inexorable pull of gravity becomes the inexorable flow of time. You can't escape the singularity any more than you can escape tomorrow. The speed of light inside a black hole still defines the light cones, but now those light cones are tilted so severely that all directions forward in time lead inward. Light emitted from inside the horizon can never escape because escaping would require traveling backward in time, which is impossible. Black holes are, in a sense, the ultimate expression of the speed of light limit. They're regions where space-time curvature makes the cosmic speed limit insufficient to escape. They're eternal prisons not because of any physical barrier, but because of the geometric structure of space-time itself. And here's something that recently became real, not just theoretical. We've actually seen the shadow of a black hole. In 2019, the Event Horizon telescope collaboration released the first image of the event horizon of the supermassive black hole at the center of galaxy. 87. That glowing ring you probably saw in the news? That's light orbiting just outside the event horizon, some of it escaping to reach us, some of it falling in. The dark center is the shadow of the event horizon itself, the boundary beyond which not even light can escape. That image is visual proof of the speed of light limit taken to its extreme. It's a photograph of a boundary in spacetime, defined by causality itself. Let's do a thought experiment. What if the speed of light were different? What if it were twice as fast, or half as fast, or infinite? How would the universe be different? If the speed of light were much slower, say 100 miles per hour instead of 186,000 miles per second, relativistic effects would be obvious in everyday life. Drive down the highway and you'd notice time running slowly in your car compared to the buildings you pass. Your GPS would be wildly inaccurate unless it accounted for your relativistic effects. You'd see objects contract noticeably in the direction they're moving. More fundamentally, atoms wouldn't work properly. Remember, the speed of light is the maximum speed of causality, the speed at which forces propagate. If light were much slower, the electromagnetic force holding atoms together would respond more sluggishly. Electrons orbiting nuclei would behave differently. Chemistry would be different. Matter might not be stable. Stars wouldn't work the same way either. The nuclear fusion in the sun's core produces gamma rays, high-energy photons that take about 100,000 years to random walk their way out of the sun's dense interior. If the speed of light were slower, this would take even longer, and stars would evolve differently. The history of the universe would be completely altered. On the other hand, if the speed of light were much faster, relativistic effects would be less noticeable at everyday speeds. But the fundamental structure of spacetime would still be the same. There would still be a finite speed of causality, just a higher one. If the speed of light were infinite, though, everything would break. Causality would be instantaneous. There would be no delay between cause and effect. Actions would have immediate consequences everywhere in the universe. But as we discussed earlier, this would create paradoxes. Different reference frames would disagree about causality in ways that create time loops. More fundamentally, if causality were instantaneous, there would be no light cones, no causal structure to spacetime. The entire concept of spacetime as we understand it would collapse. Space and time wouldn't be unified into spacetime. They'd be separate, absolute, universal. We'd be back to Newton's universe with absolute space and absolute time. But we know that universe isn't real. Experiments have proven it. The Michelson-Morley experiment, GPS satellites, particle accelerators, gravitational wave detectors, all of these confirm that spacetime is relativistic, that the speed of light is finite and constant. Some physicists have speculated that the speed of light might have been different in the very early universe, in the first fractions of a second after the Big Bang. This is called variable speed of light cosmology, and it's been proposed as an alternative explanation for some features of the early universe that are usually explained by cosmic inflation. But there's no strong evidence for this, and it remains a fringe idea. The speed of light seems to be a fundamental constant, unchanging throughout the history of the universe. It's built into the structure of spacetime at the deepest level. Changing it would mean changing the very nature of reality itself. Here's a profound thought. The speed of light is often written as c in equations, from the Latin word celeritas, meaning swiftness. But physicists who work with relativity often call it the speed of causality, or the spacetime constant. Some suggest we should stop calling it the speed of light at all, because that makes it sound like it's about light specifically, when it's really about the structure of spacetime itself. If we discovered tomorrow that photons actually have a tiny mass, so tiny we haven't detected it yet, light would travel slightly slower than the cosmic speed limit. But c, the maximum speed of causality, would remain unchanged. It's not really about light. Light just happens to travel at this speed. because photons are massless. The universe has a maximum speed for reality itself, for the propagation of existence, for the flow of cause into effect. We call it the speed of light because light got there first in our discovery of it. But it's so much more than that. Let's dive deeper into something I mentioned earlier. The speed of light is the speed of information. This is where physics meets information theory in profound ways. Information, in physics, isn't just data or knowledge. It's a physical quantity, as real as energy or momentum. When you have a system with multiple possible states, the information content is related to how many possible states there are. The more possibilities, the more information. In the 1940s, Claude Shannon developed information theory, creating mathematical tools to quantify information. At first, this was mainly useful for communication engineering, how to send messages efficiently through noisy channels. But physicists soon realized Shannon's information theory applied to physical systems too. When you measure a quantum system, you gain information about it. When entropy increases, you lose information about the detailed microscopic state. Information is conserved in fundamental physics. It can't be created or destroyed, only transformed. This is related to the reversibility of physical laws at the quantum level. But here's where it gets fascinating. Information transfer is limited by the speed of light. You cannot transmit information faster than light. This isn't just a practical limitation. It's fundamental. Think about what information really is. It's the ability to influence, to cause a change based on a state. If I send you a message saying duck, and you duck before a projectile hits you, I've used information to influence your behavior, to cause an effect at your location based on conditions at my location. The speed limit on information is the speed limit on causation itself. This connects directly to the light cone structure of spacetime. Information can only flow from the past light cone to the future light cone. Events outside your light cone can't send you information, and you can't send information to them. This has weird implications. Imagine you have a perfectly rigid rod, 1 light year long. You push one end. When does the other end move? Common sense says immediately, it's rigid, right? But that would be transmitting information faster than light. In reality, when you push one end, a compression wave travels through the rod at the speed of sound in that material, which is always slower than light. The other end doesn't move until the wave reaches it. There's no such thing as a perfectly rigid object, because perfect rigidity would allow faster than light information transfer. Now here's something mind-blowing. There's a maximum amount of information that can be contained in any region of space. This is called the holographic principle, developed by Gerard T. Hooft and Leonard Susskind in the 1990s, based on earlier work by Jacob Bekenstein on black hole thermodynamics. The holographic principle says that the maximum amount of information that can be contained in a volume of space is proportional to the surface area of that volume, measured in Planck units, not the volume itself. This is bizarre. You'd expect information capacity to depend on volume more space, more information. But it depends on surface area instead. Why? It comes from black hole physics. Bekenstein and Stephen Hawking showed in the 1970s that black holes have entropy, a measure of information, and that entropy is proportional to the area of the event horizon, not the volume of the black hole. Since black holes are the densest possible information, storage pack more information into a region, and it collapses into a black hole. This sets a universal bound on information density. 1 bit of information per Planck area, roughly. The Planck length is about 10 to 35 meters, incredibly tiny. But still, this means there's a maximum information density in the universe, and it's related to area, not volume. This suggests something profound. Maybe 3-dimensional space is somehow illusory, emergent from a 2-dimensional information structure. Maybe the universe is like a hologram, where 3-dimensional appearance emerges from 2-dimensional information encoded on a boundary. This sounds like science fiction, but it's serious theoretical physics, explored by researchers trying to understand quantum gravity, and it's all connected to the speed of light limit. The holographic principle emerges from combining general relativity, which includes the speed of light, with quantum mechanics, which includes information theory. The speed of light isn't just a speed limit on objects. It's an information limit on reality itself. It determines how quickly the universe can update, how densely information can be packed, how fast causes can propagate to effects. In a sense, the universe is a computer, and the speed of light is its clock speed. It's how fast the universe computes reality. Despite everything I've said, physicists haven't completely given up on the possibility that something, somehow, might violate the speed of light limit. Let me be clear, all evidence supports the limit. But science is about questioning, so let's explore the edge cases and loopholes. Tachyons are hypothetical particles that always travel faster than light, not particles that accelerate to faster than light speeds. That's impossible. But particles that exist only at faster than light speeds, that can never slow down to light speed or below. In special relativity, if you plug in a velocity faster than light, you get imaginary mass. Tachyons would have imaginary mass, whatever that means physically. The problem with tachyons is they'd violate causality. You could use them to send signals backward in time, creating paradoxes. Most physicists think tachyons don't exist specifically because they break causality, and the universe seems to protect causality rigorously. No experiment has ever detected a tachyon, despite people looking. Whenever something seemed to travel faster than light like neutrinos, in a flawed 2011 experiment that made headlines, further investigation has always found measurement errors. What about quantum tunneling? Particles can quantum mechanically tunnel through barriers they classically couldn't pass. Some experiments have suggested tunneling happens instantaneously, or even that particles arrive on the other side before they entered the barrier, seemingly traveling faster than light or backward in time. But detailed analysis shows that no information travels faster than light during tunneling. What happens is complex and involves the wave nature of quantum particles, but the speed of signal propagation information transfer still respects the light speed limit. Tunneling is weird, but it doesn't let you send messages faster than light. Quantum entanglement, which we discussed earlier, creates correlations faster than light, but doesn't allow information transfer faster than light. This is crucial. The universe allows faster than light correlations, but forbids faster than light causation. What about the expansion of space? Space itself can expand faster than light, and distant galaxies recede from us faster than light. But this doesn't violate relativity, because nothing is moving through space faster than light. The space between objects is growing, which is different. You can't exploit cosmic expansion to travel faster than light in any useful way. You're stuck in your local region of space, and within that region, the speed limit applies. Some theories of quantum gravity, trying to unify quantum mechanics with general relativity, suggest that spacetime might not be continuous at the smallest scales. Maybe there's a discrete structure, a spacetime foam, at the Planck scale. If spacetime is discrete rather than continuous, some people have speculated that the speed of light might not be exactly constant. Maybe it varies slightly depending on the energy of the photon. Experiments have looked for this by comparing the arrival times of high-energy and low-energy photons from distant gamma-ray bursts. If the speed of light varied with energy, photons of different energies would arrive at slightly different times after traveling billions of light years. So far, no such effect has been detected. If there is any variation, it's far smaller than we can measure. The most credible loophole, if it even is one, involves manipulating space-time geometry itself. Wormholes and warp drives don't move through space faster than light. They manipulate space to create shortcuts or moving bubbles. You still respect the local speed limit, but you effectively travel between distant points faster than light through normal space. The catch, as I mentioned, is that these solutions require exotic matter with negative energy density, and probably enormous amounts of it. We've never observed such matter. There's something called the Casimir effect, where quantum fluctuations create what looks like negative energy in tiny regions between conducting plates. But scaling this up to wormholes or warp drives would require amounts of negative energy that might not be physically achievable. There are also theorems suggesting that any method of faster-than-light travel inevitably creates closed time-like curves time machines. If you can travel faster than light in one direction, you can exploit the geometry of spacetime to return to your starting point before you left. This creates all the paradoxes we want to avoid. Stephen Hawking's chronology protection conjecture suggests that whenever you try to create a time machine, quantum effects or other phenomena intervene to prevent it. Some kind of cosmic censorship protects causality. So far, the universe seems determined to enforce its speed limit. Every proposed violation either doesn't actually work, requires impossible conditions, or remains purely theoretical with no experimental support. The speed of light stands unbroken, the ultimate cosmic law. Now let's step back and think about what all of this means philosophically. The speed of light limit isn't just a physics fact. It's a fundamental feature of existence that shapes what's possible and what's meaningful. First, it means the universe has structure, limits, rules. Reality isn't arbitrary. There are boundaries to what can happen, written into the fabric of space-time itself. This is actually profound. It means the universe is comprehensible, governed by laws we can discover and understand. Second, the finite speed of causality means that locality matters. Your immediate surroundings, your local region of space-time, is special. Events far away can't instantly affect you. You're causally connected only to things within your light cone. This gives you a kind of causal autonomy. Distant events are, in a real sense, not real to you yet. This connects to the philosophical question of existence and reality. Does something exist if it can't causally interact with anything? If there are regions of space beyond our cosmological event horizon, forever unreachable, do they exist in any meaningful sense from our perspective? Physics can't answer this. It's philosophy. But the speed of light limit forces us to confront it. Reality is local, bounded, finite from any given perspective. The observable universe is all that exists for us in terms of possible causal interaction. Third, the speed of light limit protects free will, or at least the illusion of it. If information could travel instantaneously, if the future could send signals to the past, then causality would be circular. Your choices would be both causes and effects of themselves. The flow of time would be meaningless. The light cone structure ensures that causes precede effects, that time has an arrow, that the sequence of events is meaningful. Whether you believe in free will or determinism, the finite speed of causality at least ensures that the universe has a coherent causal structure where choices lead to consequences in a logical progression. Fourth, the speed limit creates isolation and individuality. Each observer has their own perspective, their own reference frame, their own slice through space-time. There's no universal, no God's eye view of the universe. Every perspective is local, limited, individual. This might seem lonely. We're all trapped in our own reference frames, seeing our own versions of reality. But it's also empowering. Your perspective is valid. Your experience of reality is real. There's no absolute viewpoint that makes yours wrong or secondary. Fifth, the fact that light travels at finite speed means we exist in a universe with history, memory, and information. The past isn't erased. It's encoded in light, traveling outward, potentially forever. Every moment creates information that propagates through the cosmos. You are creating information right now, and that information is propagating outward at the speed of light. In a very real sense, you are making your mark on the universe in a way that can never be completely erased. The light from this moment is spreading outward, becoming part of the cosmic web of causality. This is almost poetic. The speed of light isn't just a law of physics. It's the mechanism by which the universe remembers, the way moments become permanent features of spacetime. Finally, the speed limit teaches us humility. The universe is vast, far larger than we can ever explore. Most of it is forever beyond our reach. We are tiny, local, limited beings in an incomprehensibly large cosmos. But it also teaches us our significance. We are part of this cosmos. We are made of atoms forged in stars, governed by the same laws that shape galaxies and black holes. The speed of light that defines the universe also courses through our eyes, our technology, our existence. We are not separate from the cosmos. We are how the cosmos knows itself. Despite everything we've learned about the speed of light over the past century, there are still deep mysteries. Let's explore the edge of human knowledge. The biggest mystery is the connection between quantum mechanics and gravity. We have general relativity, which beautifully describes gravity and spacetime, including the role of the speed of light. We have quantum mechanics, which beautifully describes the behavior of particles in fields. But these two theories are mathematically incompatible at the deepest level. Quantum mechanics describes reality as fundamentally probabilistic and discrete. General relativity describes spacetime as smooth and deterministic. When you try to combine them to create a theory of quantum gravity, you run into infinities and paradoxes. String theory is one approach to solving this. It suggests that particles are actually tiny vibrating strings, and spacetime itself emerges from the interactions of these strings. In string theory, the speed of light emerges as well. It's not put in by hand. It's a consequence of the string dynamics. Loop quantum gravity is another approach. It suggests that spacetime itself is quantized, made of discrete loops at the Planck scale. The smooth spacetime we experience is an approximation, like how a computer screen looks smooth but is actually made of pixels. In loop quantum gravity, the speed of light relates to how these quantum loops connect and update. Neither theory is proven. We don't have experimental evidence that can distinguish between them or confirm either one. The energies required to test quantum gravity directly are far beyond what we can achieve in particle accelerators. We're stuck with indirect clues and mathematical consistency. But here's what's fascinating. In both approaches, the speed of light isn't fundamental. It emerges from something deeper. Spacetime itself emerges. Reality as we experience it is somehow constructed from more fundamental building blocks. If this is true, then asking why does light have a speed limit is like asking why does water have waves? The answer isn't about water molecules individually. It's about emergent behavior of many molecules interacting. Similarly, the speed of light might be an emergent property of the fundamental structure of reality. Another mystery, dark energy. The universe's expansion is accelerating, driven by some kind of energy that permeates space itself. We call it dark energy, but we have no idea what it is. It makes up about 68% of the universe's total energy content. Dark energy doesn't violate the speed of light limit, but it does affect how that limit plays out on cosmic scales. The acceleration of expansion means more and more galaxies are slipping beyond our cosmological event horizon. The causal structure of the universe is changing over time. Some theories suggest dark energy might be the energy of empty space itself, quantum fluctuations creating a kind of vacuum energy. But when you calculate how much vacuum energy there should be based on quantum mechanics, you get a number that's 10,120 times larger than what we observe. That's one with 120 zeros. It's the worst prediction in the history of physics. Why is vacuum energy so much smaller than theory predicts? We don't know. This is called the cosmological constant problem, and it's one of the deepest mysteries in physics. And it's intimately connected to the structure of spacetime and the speed of light. Another cutting-edge area, the black hole information paradox. When a black hole evaporates via Hawking radiation, a process where quantum effects cause black holes to slowly emit particles and shrink. Where does the information about everything that fell into the black hole go? Hawking radiation appears to be completely thermal, completely random, carrying no information about what fell in. But quantum mechanics says information can't be destroyed. So we have a paradox. Either information is destroyed, violating quantum mechanics, or it somehow escapes the black hole, violating general relativity's claim that nothing can escape a black hole. Recent work suggests the information might be encoded in subtle correlations in the Hawking radiation, or that it might be stored on the event horizon itself in a holographic way. This connects back to the holographic principle I mentioned earlier. The speed of light is at the heart of this paradox, because the event horizon is defined by light cones, by causality structure. Solving the information paradox requires understanding quantum gravity, which brings us back to the fundamental nature of spacetime and the speed of light. It's all connected. Here's another frontier, the possibility of extra dimensions. String theory requires 10 or 11 dimensions of spacetime, not just the 4 we experience. Where are these extra dimensions? The standard answer is they're curled up tiny, too small to notice, compactified at scales near the Planck length. But what if some extra dimensions are larger, just hidden from us in some other way? What if our 3-dimensional space is like a membrane floating in a higher dimensional space? This is called brane theory, and it suggests that gravity might leak into these extra dimensions, which could explain why gravity is so much weaker than the other forces. If extra dimensions exist, does the speed of light limit apply in those dimensions too? Can particles or fields shortcut through higher dimensions to effectively travel faster than light in our 3-dimensional space? These are open questions that we don't have answers to yet. Experiments at the Large Hadron Collider and other facilities are looking for signs of extra dimensions, but so far, nothing. If they exist, they're well hidden. One more mystery. The arrow of time. The laws of physics are almost entirely time-symmetric. They work the same forwards and backwards in time. Yet we experience time flowing in one direction. The past is fixed, the future is open. Eggs break but don't unbreak. We remember the past but not the future. Why? The standard answer involves entropy, the second law of thermodynamics. Entropy increases over time, creating an arrow pointing from low entropy past to high entropy future. But why was entropy so low in the early universe? Why did the universe start in such a special low entropy state? This is called the past hypothesis, and we don't have a good explanation for it. It might be related to the initial conditions of the Big Bang, or to quantum gravity effects in the early universe, or to the multiverse. Maybe we observe low entropy because only such universes can support life and observers. And this connects to the speed of light, because the light cone structure, the causal structure of spacetime, is what gives time its directionality. Without a speed limit on causality, time wouldn't have an arrow. The finite speed of light helps create the distinction between past and future. Every one of these mysteries, quantum gravity, dark energy, black hole information, extra dimensions, the arrow of time involves the speed of light at some level. It's all interconnected. Understanding why light has a speed limit is ultimately about understanding the deepest structure of reality itself. We're not there yet, but we're working on it. Let me ground all this theory with the real experiments that confirm the speed of light limit and its consequences. Because this isn't just math and speculation. It's experimentally verified reality. In 1971, Joseph Haffel and Richard Keating did something brilliant and simple. They took 4 cesium atomic clocks, flew them around the world on commercial airliners, and compared them to clocks that stayed on the ground. The flying clocks, moving relative to the ground and at different gravitational potentials, experienced time differently. When they landed, the clocks showed different times. The eastward flying clocks lost about 59 nanoseconds compared to the ground clocks. The westward flying clocks gained about 273 nanoseconds. These differences match the predictions of special and general relativity almost perfectly. Time dilation and gravitational time dilation were directly measured with atomic clocks on airplanes. You might think, that's tiny, just nanoseconds. But those nanoseconds matter. GPS satellites have to account for nanosecond-level timing differences, or they'd be useless. Every time you navigate with GPS, you're proving relativity is correct. In particle accelerators, we accelerate particles to incredibly high speeds and watch them behave exactly as relativity predicts. Muons are particles that normally decay in about 2.2 microseconds. But when we accelerate them to 99.94% the speed of light, they last about 29 times longer from our perspective because of time dilation. The muons experience their normal 2.2 microseconds, but we see them living much longer because time is passing more slowly for them. This has been measured thousands of times. It's not controversial. It's basic experimental physics, and it confirms that time dilation is real. In 2017, the LIGO gravitational wave detectors observed gravitational waves from two colliding neutron stars. About 1.7 seconds after the gravitational wave signal, the Fermi Gamma Ray Space Telescope detected a burst of gamma rays from the same event. The signals traveled 130 million light-years to reach us. The fact that the gravitational waves and electromagnetic waves arrived within 1.7 seconds after traveling for 130 million years tells us that they travel at nearly identical speeds. Gravity propagates at the speed of light, just as general relativity predicts, to within about 1 part in yp. That's extraordinary precision. Tests of special relativity have gotten incredibly sophisticated. The Michelson-Morley experiment has been repeated with modern equipment thousands of times more sensitive than the original. Every single test confirms that the speed of light is the same in all directions, regardless of the Earth's motion. Experiments have tested whether the speed of light depends on the light's frequency, or the source's motion, or the gravitational field it's in. Every test confirms that c is constant. We've sent spacecraft to other planets and used their radio signals to test relativity. The Cassini spacecraft orbiting Saturn provided one of the best tests of general relativity when radio signals passing near the Sun were delayed by the Sun's gravity, exactly as predicted. The Pound-Rebka experiment in 1959 measured gravitational redshift light. Climbing out of a gravitational field loses energy and shifts to longer wavelengths. They did this in a tower at Harvard with just 22.5 meters of height difference and confirmed general relativity to about 1% precision. Modern versions of this experiment confirm it to 1 part in 107. Every single experimental test of relativity has confirmed it. No exceptions. The speed of light is constant. Time dilation is real. Length contraction is real. Mass energy equivalence is real. Causality is limited to light speed. This is not speculative theory. This is experimentally verified fact, confirmed by thousands of experiments over more than a century. And here's what really drives it home. All of modern technology relies on relativity being correct. GPS wouldn't work without accounting for both special and general relativistic effects. Particle accelerators, like the LHC, couldn't function if we didn't account for relativistic mass increase. Synchrotron radiation facilities that produce X-rays for materials science and biology research rely on relativistic electrons. Your cell phone, your computer, medical imaging equipment, scientific instruments, all of them rely on physics that emerges from the speed of light being constant and finite. The speed of light limit isn't just true in theory. It's true in practice, embedded in every piece of technology that depends on precise timing, high-speed particles, or electromagnetic radiation. Reality really works this way. Let me take you on an imaginary journey to really make this tangible. Imagine you're on a spacecraft and you're going to accelerate to very close to the speed of light. You start accelerating at 1 gram, the same acceleration as Earth's gravity, so it feels comfortable. Days pass, weeks pass, months. You're continuously accelerating, getting faster and faster. After about 1 year of accelerating at 1 gram, you're traveling at about 77% the speed of light relative to Earth. Time dilation has become noticeable. Your clocks are running at about 64% the speed of Earth clocks. For every 10 days that pass for you, about 16 days pass on Earth. You keep accelerating. After 2 years of constant 1 gram acceleration from your perspective, you're at about 97% light speed. Time dilation is dramatic now. Your clocks run at about 25% of Earth time. Every month for you is 4 months on Earth. A universe ahead of you looks strange. Light from stars in front of you is blue shifted, compressed to higher energies and frequencies. The stars behind you are red shifted, stretched to lower frequencies. Due to aberration, stars seem to cluster toward the direction you're traveling. The cosmic microwave background radiation, normally in the microwave range, is blue shifted to higher energies in front of you. After 3 years of your time, still accelerating at 1 gram, you're at 99.6% light speed. Time dilation is extreme. 1 year for you is nearly 7 years on Earth. If you could look back and see Earth in real time, you'd see time flowing nearly 7 times faster there. But you can't see Earth in real time. The light you're seeing from Earth left Earth in the past. And due to your motion, even that light is heavily red shifted. Earth appears to recede into the past, its light stretched and dimmed. After 5 years of your time accelerating at 1 gram, you're at 99.97% light speed. 1 year for you is about 40 years on Earth. Friends and family you left behind are aging rapidly from your perspective. By the time you've subjectively experienced 5 years, about 85 years have passed on Earth. The distances you're covering are enormous. At these speeds, you could reach nearby stars in years of your time, even though they're many light years away, because length contraction shrinks the distance you need to travel. The 4.2 light years to Proxima Centauri is contracted to a few months of travel at your speeds. From Earth's perspective, you're still moving slower than light, and it's taking you more than 4.2 years to reach Proxima Centauri. But from your perspective, the distance is shorter, so you get there faster. Both perspectives are correct. This is the nature of spacetime. Now imagine you decelerate, turn around, and come back to Earth. The round trip takes perhaps 10 years of your subjective time. When you arrive back at Earth, you step off your spacecraft to find that centuries have passed. Everyone you knew is long dead. Civilizations have risen and fallen. You've traveled through time into Earth's future. This is the twin paradox, and it's not a paradox at all. It's a real consequence of time dilation. The traveling twin ages less because they accelerate and change reference frames. The symmetry is broken. Time dilation is real, and it has real consequences. This isn't science fiction. This is what would actually happen if we could build such a spacecraft. The physics is well understood. The only obstacle is technological. We can't accelerate large spacecraft to relativistic speeds with current technology. But the physics allows it. The universe allows it. You could, in principle, travel to distant parts of the galaxy and return to Earth, experiencing only decades of time while millennia pass on Earth. You could see the far future, but you could never return to your own time. The speed of light protects causality. You can travel forward in time by moving fast, but you can never go back. Here's something beautiful that I want you to appreciate. The speed of light connects everything in physics. It's not just a fact about light or motion. It's the linchpin that holds all of modern physics together. The speed of light connects space and time into spacetime. It connects matter and energy through E equals mc. It connects electricity and magnetism into electromagnetism. It connects classical physics and quantum physics through quantum field theory. It connects gravity and spacetime through general relativity. Let me show you how deep this goes. In the 1860s, James Clerk Maxwell unified electricity and magnetism into a single theory, electromagnetism. His equations describing electric and magnetic fields predicted that electromagnetic disturbances would propagate as waves. When he calculated the speed of these waves from the strengths of electric and magnetic forces, he got about 310,000 kilometers per second. He recognized this was the speed of light. Light was an electromagnetic wave. Electricity, magnetism, and light were all aspects of a single unified phenomenon. The speed of light emerged from the fundamental constants describing electric and magnetic forces. This was one of the greatest unifications in physics. Three apparently separate phenomena, electricity, magnetism, light, were revealed to be one thing. And the speed of light was the key that unlocked this unification. Later, special relativity showed that space and time were also unified. They're not separate entities, but aspects of spacetime. And the speed of light is the conversion factor, the exchange rate between space and time. In quantum field theory, which unifies quantum mechanics with special relativity, particles are excitations of quantum fields. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. These fields exist throughout spacetime, and their excitations propagate at speeds up to and including the speed of light, depending on the particle's mass. Quantum field theory explains all three of the fundamental forces we understand well: electromagnetism, the weak nuclear force, and the strong nuclear force. All of them respect the speed of light limit. All of them fit into the relativistic spacetime framework. The fourth force, gravity, is described by general relativity, which also respects and incorporates the speed of light. Gravity is the curvature of spacetime itself, and changes in that curvature propagate as gravitational waves at the speed of light. Everything fits together. The speed of light isn't some arbitrary constant that we have to plug into different theories separately. It's woven into the structure of reality at every level. Remove it or change it, and the entire edifice of physics collapses. This unity suggests something profound. The universe is fundamentally comprehensible. It's not a collection of random facts, but an integrated whole governed by consistent principles. The speed of light is one of those principles, perhaps the deepest one, connecting everything else. This gives me hope about the remaining mysteries. We don't yet have a theory of quantum gravity that successfully unifies quantum mechanics and general relativity. But I believe we'll find it, because the universe keeps revealing deeper unities every time we look. The speed of light connected electricity and magnetism. It connected space and time. It connected matter and energy. It connected quantum mechanics and relativity into quantum field theory. What's one more unification? What pattern are we still missing that will connect quantum mechanics and gravity and reveal an even deeper truth about reality? When we find it, I guarantee you the speed of light will be at the center of it. We're nearing the end of this journey, so let me bring this all back to you, personally, and why understanding the speed of light matters for your life. You might think, I'm not a physicist. I'll never travel near light speed. Why should I care about relativity and spacetime? Here's why. Understanding the speed of light changes how you see reality. It reveals that the universe is far stranger, far more beautiful, far more unified than everyday experience suggests. It shows you that your intuitions about space, time, and causality, intuitions built from everyday experience, are wrong in deep and fascinating ways. When you look at the night sky now, knowing what you know, you're not just seeing stars. You're seeing photons that have traveled for years, decades, centuries, or millennia to reach your eye. You're seeing the past, directly, tangibly. You're connected to ancient light, to events that happened when your ancestors were living in caves, or when dinosaurs roamed Earth, or before Earth even existed. Every photon entering your eye is a messenger from the past, carrying information encoded in its energy and direction. Your brain reconstructs this information into an image, a model of reality. But what you're seeing isn't the present. It's a patchwork of different moments in time, assembled from light that left different stars at different epochs. You are a time traveler, receiving messages from the past with your eyes. When you talk to someone, your words take time to travel through the air as sound waves. When you video call someone on another continent, your image and voice take time to travel as electromagnetic signals through fiber optic cables and satellites. There's a delay, usually imperceptible, but it's there. You're never truly experiencing now with anyone not in your immediate presence. You're always slightly out of sync with the rest of the world. This isn't a technological limitation. It's a fundamental feature of reality. Simultaneity doesn't exist except locally. Understanding this gives you a kind of cosmic humility. You're not the center of the universe with an absolute perspective on reality. You're one observer among countless possible observers, each with their own equally valid frame of reference, each experiencing their own version of time and space. But it also gives you cosmic significance. Your reference frame matters. Your perspective is real. You're not experiencing a shadow or illusion of reality. You're experiencing reality itself from your location in spacetime, which is as real as any other location. The speed of light teaches you that limits aren't necessarily limitations. The speed limit isn't a frustrating barrier keeping us from exploring the universe. It's the fundamental structure that makes the universe consistent, comprehensible, causal. Without it, reality would be paradoxical, and existence might be impossible. Constraints create meaning. The finite speed of light creates the arrow of time, the distinction between past and future, the possibility of change and growth and learning. Without limits, nothing would matter because everything would be possible, all at once, in a timeless, causeless blur. You exist because the universe has structure, and the speed of light is a key part of that structure. Finally, understanding the speed of light connects you to the greatest intellectual achievement of humanity, physics. We've figured this out. We, tiny beings on a small planet, have discovered the deep rules that govern reality. We've measured the speed of causality itself. We've probed the structure of spacetime. We've unified forces and discovered that mass is energy and that time is relative. This is astounding. You should feel proud to be part of a species that accomplished this. And you should feel empowered, because if we can understand something as counterintuitive and profound as relativity, what else might we figure out? The speed of light isn't just a physics fact. It's an invitation to see reality as it truly is, strange and beautiful and deeply interconnected. So, why does light have a speed limit? The deepest answer is, light doesn't have a speed limit. Reality does. Causality does. Space-time itself does. Light just shows us this limit because photons, being massless, travel at the maximum possible speed through space-time. The speed of light is really the speed of causality, the maximum rate at which causes can propagate to effects, the fundamental clock speed of the universe. This limit exists because space and time are unified into space-time, and motion through space is rotation in space-time, converting motion through time into motion through space. You're always moving through space-time at the speed of light, but that motion can be divided between time and space in different proportions. The limit protects causality, prevents paradoxes, creates the arrow of time, defines what can influence what, and makes the universe consistent and comprehensible. It emerges from the deepest structure of reality, from quantum mechanics and relativity, and possibly from even deeper theories we haven't fully developed yet. It connects everything in physics, space and time, matter and energy, electricity and magnetism, quantum fields and particles, gravity and spacetime curvature. And it reveals that the universe is far stranger than everyday experience suggests, but also far more unified, more elegant, more beautiful than you might have imagined. You've just spent nearly 4 hours exploring one of the deepest mysteries in physics. You've journeyed from simple observations of Jupiter's moons to the structure of spacetime itself, from atomic clocks on airplanes to the event horizons of black holes, from the mathematics of relativity to the philosophical implications of causality. You now understand something profound about reality that most humans throughout history never knew. The speed of light isn't arbitrary, it's fundamental. And understanding it changes everything. If this video expanded your mind, if it made you see reality differently, if it sparked wonder and curiosity, hit that like button. Share this with someone who's ready to have their understanding of the universe transformed. Subscribe, because we're going to keep exploring the deepest mysteries of existence together. And remember, every time you see light, whether from the sun, a star, or your screen, you're witnessing the cosmic speed limit in action. You're seeing the fundamental constant that holds reality together. Light doesn't just have a speed limit. Light reveals the speed of existence itself. Thanks for joining me on this journey through spacetime. Until next time, keep questioning, keep wondering, and keep looking at the universe with fresh eyes.